So I should apologize for being a condensed matter theorist, not very mathematically minded. So I will use many heuristic arguments. And so please don't hesitate to interrupt me to have eventually some more details about the physics I will be discussing. So I plan to present you 3 topics. The first one is the fractional quantum Hall effect. That I will briefly describe, and the aim of this part is to introduce a new object, a new particle, which is called a composite fermion. So in some sense that I will try to render rather precise, this is a quasi-particle, which is some kind of dressed electron with a dressing which is not perturbative. And it gives us a quantitative picture of the so-called fractional quantum Hall effect by using explicit many-body wave functions that are both explicit and mysterious. And that's certainly a topic that deserves further study, which I will try to give you some feeling I have about that. So that's the first part. So this composite fermion called by some a theory. So, oui. Okay, voilà. So you will decide if this is a theory for you or just some kind of heuristic stuff, which is maybe not completely meaningful. So anyway, this has to do with really the many-body problem. It's really a problem of interacting particles. So the second part will be devoted to a phenomenon which happens only with the real electrons on holes. So it's what is known as interlayer phase coherence. So that's a phenomenon of quantum phase coherence, which is some kind of exciton condensation under a magnetic field. And the particles that undergo this condensation are really simple electrons and or holes, if you like. So it's not the same kind of physics that happens in the fractional quantum Hall effect. This kind of phase coherence leads to various phenomena that are very closely related to superfluidity, so I will describe a bit the phenomenology of this. And then you can guess what the third part is about, is that quite recently it has been observed that you can have this interlayer phase coherence happening for states involving composite fermions. So it's a second many-body physics that happens to quasi-particles that are themselves emerging quasi-particles. So interlayer phase coherence of composite fermions. ILC will be interlayer phase coherence with composite fermions. So I will tell you a few words about the phenomenology of this coherence, which involves also super phenomena in the sense of superfluidity, superflow, and the like. And I will try to see how we can try to take the best knowledge we have of the fractional quantum Hall effect, which is these explicit wave functions coming from the composite fermion theory, and how to try to apply them to the description of the interlayer phase coherence of composite fermions. So relation with wave functions. So to give you an idea of the time scale, this is pretty old now, this composite fermion description of the fractional quantum Hall effect. It dates back from the 90s, essentially. The interlayer phase coherence has been studied in detail in bilayer of semiconductors. Okay. Let me let me try to move the blackboard. So up. Ah, okay. No, sorry. Number one is here?
Number one is the first one in front, yeah. You can move up.
Ah, tableau one. Okay, I see. So just, okay. Okay. Voilà. Thank you. So this is the 90s. This is approximately also the 90s. And this ILC with composite fermions was discovered experimentally in 2019. In two very nice experimental papers. So this is pretty new physics, recent physics. So the fractional quantum Hall effect I will describe a bit happens in many materials that are two-dimensional. And I will essentially concentrate on semiconductor realizations of 2D electron gases. The interlayer phase coherence is a phenomenon that happens also under a magnetic field, something I have not yet said, I think. So this is exciton condensation under a magnetic field. It's a real proper exciton condensation, but it's at non-zero magnetic field. This has been observed in bilayer systems of two-dimensional electron gases in gallium arsenide semiconductors. And finally, the interlayer phase coherence of composite fermions. So the most interesting moment of this session. This was observed in layers under a magnetic field of graphene systems. So I will just say a few words about that, but in graphene samples, we can also create bilayers with two-dimensional electron gases in a regime which is slightly different from the case of semiconductors, and this allows precisely to probe this special regime of ILC for composite fermions. So I will not show you any experimental details, which is bad, but that's the rule of the game. So I will try to write a bare minimum of equations to illustrate this amusing story. So the first thing I have to describe before embarking for the fractional quantum Hall effect is a reminder of the integer quantum Hall effect. Sorry for that, but I don't see how I can do that without telling you a few things about the integer quantum Hall effect. Ah, sorry. Up. Okay. So we will discuss the properties of two-dimensional electron gases. So the electrons are confined to essentially a 2D plane, and they are under the action of a perpendicular uniform magnetic field. If you solve this simple quantum problem, you find that the kinetic energy is frozen, becomes simply a constant, and the energy levels form Landau levels. So I will not make the detailed calculation, which is quite simple. If you have a uniform magnetic field, then you can form a vector potential which is 1/2 of B cross R being the distance in the plane. And then the kinetic energy of the electrons is replaced by the addition of the vector potential. This is called the symmetric gauge, and is certainly adapted to situations in which you don't mind about the boundaries. Let me draw the energy spectrum. So this axe is the energy. Solving this simple quantum mechanical problem, which is one body, you find a set of energy levels separated by a characteristic energy which is h bar omega c. Omega c is the cyclotron frequency, which is EB charge times B divided by the mass. These Landau levels are regularly spaced, and the energy of these is an integer plus 1/2 times h bar omega c. These levels are degenerate with a degeneracy which is proportional to the magnetic field. Degeneracy of the Landau levels. So it's proportional to the area on the magnetic field, and the degeneracy, it's simply the number of flux quanta through the sample, which means that, so it's the flux, B times the area of the sample, divided by the unit of flux you can cook up with the Planck's constant of the electric charge, so E over H divided by the electric charge. That's the one-body picture, and in the first part of this talk, I will not discuss the electron spin, so we will imagine that we are concentrating on situations in which you are just dealing with spin-polarized situations. Then spin will play a major role in this interlayer coherence stuff, so here without spin. So if you increase B, what happens? It means that these levels are more and more separated by larger energies, and the number of states in each level increases with B. So if you have a sample with a finite number of electrons, and you tune B to larger values, it means that the levels are more and more separated, and you have more and more states available in each level. So if you construct the ground state just by filling these orbitals, it means that at some point you will arrive in a situation in which only the lowest Landau level is completely filled and all the others are essentially empty at 0 temperature. So this is a very crude situation that will not describe simple samples. There are, of course, many deviations from this. You can imagine that in a real case, if you look at the density of states as a function of the energy, certainly these levels that are exactly degenerate will give you some peak in the density of state. So certainly, I will use just another color, but the same figure. So the density of state should have peaks centered at these magic values. Between the peaks, so there are regions with very small density of states, and you will have a gap to excitations between these states, which is governed by this cyclotron energy. Starting from this, and this I will not show in detail, we are in the situation of the integer quantum Hall effect when the Fermi level happens to be between such peaks, in which case the Hall resistance is only governed by the number of field levels, those for which the density of states is maximal. And there is a gap between these peaks that will give rise to phenomenon in which you have no dissipation because simply the gap will forbid dissipation. So no dissipation for a very simple physical reason. Dissipation. And something which I will not explain in detail, you have quantized Hall resistance. Okay. Up. Okay. So let me introduce the filling factor, which I will use repeatedly. So the filling factor, it's simply the number of electrons that you put in a given Landau level. So I will decide this to be the number of electrons divided by the number of states in a Landau level. So it's the number of flux quanta, which with these formulas can be written as the areal density, so simply the number of electrons divided by the area, times Planck's constant divided by the charge on B. So that's the filling factor, and this integer quantum Hall effect will arise each time this quantity is equal to some integer. Now it's a very convenient measurement in semiconductor physics to measure the Hall voltage, which is done in the following way. Imagine that you have a sample which has more or less the shape of a bar. You impose a current along the bar, and you measure the voltage across the sample. Not along the sample, but across the sample. In fact, in the integer quantum Hall regime, if you measure the voltage drop along the sample, so between two such points, you find that it is zero, simply because there is no dissipation mechanism available. So there is no voltage drop along the sample, but there is a Hall voltage. So the Hall voltage, classically, it's given simply by, let me see, the Hall resistance times the intensity of the current. That's the current which I force through the sample. And if you make a classical model, this Hall resistance, it's simply the magnetic field divided by density times the electric charge. And this is the Hall resistance, what we call the Hall resistance. That's simply what you can get from a simple Drude model in which electrons are treated classically. They undergo cyclotron motion due to the Lorentz force. And if you impose a current, then they are deflected by the magnetic field, and this will create a potential across the sample. So that's a very simple calculation that you can do that gives us this resistance. And if I take this Hall resistance and I decide that the value of B is such that we are right at the condition for the integer quantum Hall effect, then this Hall resistance is 1 over an integer, this integer, so nu, times h divided by a squared, using the formula for the classical Hall effect and the value of the filling factor, with nu an integer. So that's fine, it looks very classical, but in fact what is not classical is that this Hall resistance happens to be quantized for values when the magnetic field deviates from the perfect filling of the Landau level, which means in fact that all these states are localized and do not participate in the conduction properties. So if I make a drawing of the Hall resistance as a function of B, so the classical formula is just B divided by density times electric charge, so it should be a straight line. And I claim that when you go at very low temperatures and you enter the quantum Hall regime, and then you start to feel the discreteness of the Landau level, then you see that there are plateaus and these plateaus are all given by formulas 1 over an integer. Maybe I should not call it n but p, let's say, because I used n for the density, times h divided by e squared. That's fine. And that's an explanation which is based on one-body physics plus disorder. And it gives us a satisfactory explanation for the integer quantum Hall effect. Experiments tell us that there is more to physics than this simple effect. Well, not that simple after all. Huh? And there is also the appearance of plateaus at fractional values. So there are plateaus for fractional filling of the lambda levels. The most striking case happens for filling factor 1/3. So with a Hall resistance, which is 3 times h over e squared, which means that it happens to be which is much larger than the case of all integer filling factors. So that was a bit of a surprise. When you are at B larger than the last plateaus, it means that you just have some electrons filling the lowest lambda level, and that's all. In the case of the simple parabolic dispersion relation that I wrote, there is a minimum energy in this business. So you just have electrons partially filling this. If you were to use a naive reasoning, you could expect that you should observe something like some Fermi liquid, some 2D Fermi liquid, maybe correlated, but in a region where you have a rather high density of state. But this is not at all what happens. You find again a quantized Hall resistance and a regime in which there is no dissipation. Again, if you measure the voltage along the sample, then you find that there is no voltage drop. There are no channels for the electron motion to dissipate. So what do we know about this striking phenomenon? I need for that no. Yes, okay, I see. Okay, down now. Okay. We need wave functions. I wrote the energies. Okay, so I will write down the wave functions for these lambda levels, especially for the lowest lambda level. I told you that it's convenient to, well, one possibility is to use the symmetric gauge to solve for the kinetic energy quantum Hamiltonian. If you do this, you can, of course, compute the wave functions. Let me write z, which is x plus iy, so the complex coordinate in the 2D plane of the electron gas. Then the lowest lambda level is spanned by wave functions that we can write as z to the m, e minus square modulus of m over 4L squared, where m is an integer which is positive or 0. And this quantity L, it's a length which is called the magnetic length. The characteristic length you can cook up with the parameters in the problem. L, which is square root of h bar divided by EB. So for large B, it becomes very small. And this is, again, ignoring spin. I'm just discussing the case of full spin polarization. OK. So this is a one-body wave function. And this is an integer. So what is the formula for an arbitrary many-body state? Then it's very easy to guess. Well, not to guess, to demonstrate. If you have n electrons, you will make a sum of products of such wave functions, which means that it should be a polynomial in the z variables times E minus the sum of zi squared divided by 4L squared. And this polynomial should be antisymmetric because electrons are fermions and spin is polarized. So that's just the statement that this is a state which is in the lowest Landau level. So wave function for the lowest Landau level. So in general, it's not a very useful approach to try to write down the wave function of a many-body problem. There are exceptions, like the BCS wave function, that give us a very good approach to the solution of the true problem. And the same happens in the case of the fractional quantum Hall effect, because for the filling factor 1/3, Laughlin decided to write down a proposal wave function for describing the many-body ground state of electrons at filling factor 1/3 with a very simple wave function, which is called, after him, the antisymmetric polynomial that you use here. It's simply the product of zi minus j cube times the same Gaussian factor. So it's, of course, exactly of the form that we wrote before. You have a polynomial, and then you have this universal Gaussian factor because it happened, it happened in all one-body wave functions. So fine. So that's a many-body wave function, which is close to the solution of the true many-body state. I will call it an excellent solution to the problem. Why is that so? A few remarks, simple remarks, but nevertheless worth doing them. So here you put a cube. Okay. So I decided to put a cube. It should be an odd integer because you want antisymmetry of the wave function. And in fact, this factor governs the filling factor. If you compute let's say, you take this wave function and you make a plot of the density of this guy. So there is a finite number of electrons. So it occupies a finite region in space. It has circular symmetry because you can simply rotate all z coordinates by the same phase. And if you draw the density of this state, you find that, so this is rho, this is the radius. You find that apart from some oscillations at some boundary, it's a flat pancake, which is circular. That's the shape of the density. And if you compute the density, there are many ways to do that, numerically, or there is a trick if you like plasma physics. Anyway, it doesn't matter. You find that the density is 1/3 when you are in the middle of this disk. Of course, at very large distances, then everybody is killed by the Gaussian, and that's it. But inside, you have a very nice flat region in which the density is very well defined. If I put a 2, you see, then it's a decent approximation for bosons. It's even an exact ground state if we believe that bosons have only S-wave interactions. So that's fine if you are doing atomic gases at bosonic at very low temperatures. If I put another odd integer, like let's say 5, then 5, it means that you guess that the same calculation will give us a state with a smaller density. In fact, the filling factor that this state has is 1/5. So this power is the inverse of the filling factor. It's not obvious. It has to be calculated by a means of simple or complicated things, if you are lucky or not. So we know that this state has the correct phenomenology to explain the fractional quantum Hall state. That's, of course, the least one wants. correct phenomenology. And then you want theory, of course. So this is not the ground state of the correct Coulomb interaction between electrons, but the best one can do, which I will not describe in detail, is that if I look at the Coulomb Hamiltonian projected in the lowest Landau level, when it is projected in the lowest Landau level, then it has a form which is simplified, and you can write it down as a sum of all pairs of particles. It's a two-body interaction of some numbers times the projector of a relative moment, angular momentum m. So ij, that's the index of the pair, and then there is a sum on the relative angular momentum from 0 to infinity. In fact, if we are dealing with spinless fermion, it's only odd powers that are allowed. And the relative angular momentum, it's simply the power when you expand your polynomial in terms of the relative distance between the particles, you will find powers, odd powers because of antisymmetry, and that's simply the relative angular momentum. So the Coulomb Hamiltonian, or in fact, any two-body interaction is of this form. And if I drop all these coefficients and just take V1, then it's very simple to see that this Laughlin wave function it's the exact ground state of the two-body interaction in which I just keep interaction in the relative angular momentum 1. And it's a zero energy ground state simply because if you develop this as a polynomial in Zi minus Zj, then it starts with power 3 and higher powers. So if I just keep relative angular momentum 1 in the Hamiltonian, then this is an exact zero energy state. So it's not the exact ground state of the Hamiltonian you want, but you can argue that maybe this Hamiltonian is not that far from Coulomb, and we all believe that it's not that far from Coulomb. So that's, let's say, that's an introduction to the field of this fractional quantum business. So that's fine. We can, of course, spend a lot of time proving that there is some adiabatic continuity between this projected special Hamiltonian and Coulomb. But there is something else that I will advertise, which is the construction of composite fermions. And the reason is very simple, is that this is an explanation which is, of course, strictly limited to filling factor 1/3 or 1/5, and so on. But nature reveals that there are many fractions that are not 1 over an integer, but there are many fractions like 2/5, 3/7, 4/9, and so on. So they are not directly explained by this Laughlin wave function, so we need to do something better. Hop, voilà. So I will rewrite. Okay. Okay. It's not bad, this system. Okay. So let's take the Laughlin wave function and let me write it in another way. The power of 3, I can write it as the product of Zi minus Zj times 1 times the product of I distinct of j of Zi minus Zj up to some sign, okay, with a power 1, so that this is simply the product of two factors, I smaller than j and j smaller than I, okay? So that's simple algebra. Let me look at this. This product of factors, in fact, it's a very famous determinant. It's the Vandermonde determinant. So the van der Monde determinant, it's a determinant which involves exactly n variables with powers ascending up to n minus 1. So in the first column of the matrix that I will write here, you use coordinate z1 from power 0, 1, 2, 3 up to n minus 1. In the second column, you do the same for z2. Z2 to the n minus 1. And then you go till the nth particle, and you use the same powers. That's a determinant which can be computed. That's a very nice exercise. And the result of that is up to a sign which we don't care about signs in this talk, of course. This is the product of zi minus zj. So you see that this Laughlin wave function for m equals 3, it's the van der Monde determinant multiplied by this factor, zi minus zj, I different from j. Now let me do the following trick. This product, as you see, I can see it as the product over I of products over j. I will distribute all these products inside the determinant and write it as follows. So psi Laughlin m equals 3. So let me write the first element here. It's the product of a j different from 1 of z1 minus zj times 1, then z1 times the same factor, up to the power n minus 1. So you see what's going on. Instead of repeating stupidly the same factor, I will give it a name, so j, with an index which is the number of the particle which is inside, so that's g1. So in the second column, I will have g2, z2 times g2, z2 squared times g2, and so on, up to z2 to the n minus 1 j2. And this goes on till the particle number n. So you see that it looks like a it's not that it looks, it is a determinant, but now I've decided to change it gives us a hint that we can change the rule of the game. You see that it's a determinant of wave functions between quotes in which you replace the z to the m by z to the m times this factor j. Which is the product of z minus the coordinates of all the other particles. So it gives us a very simple idea, is that maybe we can play the same game of filling one-body orbitals, provided we just change the definition of orbitals and we include correlations in the definition of orbitals. So instead of playing with these one-body orbitals, we will play the same game with such orbitals, which means that we can do all the reasonings we do like in chemistry, in which you put simply electrons in boxes, and the boxes are defined by this. And we decide to call this the game of composite fermions. When they are occupying such orbitals, they are called composite fermions. Composite due to the appearance of this which we will call a Jastrow-like factor, because the Jastrow correlation functions were introduced not in the context of the Landau level physics, but in a way to include correlations in many body wave functions. So that's the idea of making composite fermion wave functions. But for the time being, I just decided to write in a complicated manner the Laughlin wave function. So what can we do as? So the reasoning goes as follows. If you decide to use these modified orbitals, you see that this is just filling factor unity for the composite fermions, because it's exactly, if you look at this Slater determinant, the van der Monde determinant, then you have filled exactly all orbitals from n equal to 0 to n equal n minus 1. You have decided to fill them exactly up to some maximal value. So this is the picture which underlies a completely filled shell, like the van der Monde determinant, where this is z to the 0, z1, and z to some maximal power. Now, I don't put arrows on the vertical bars. That would be the spin, but anyway, okay. So if you decide to change the rule of the game, you see that, again, you can think of this as a filled shell. So you can decide that the filling factor of the composite fermion, which I write as nu star, it's 1. So it's exactly equivalent if I take the definition of the filling factor, which is written maybe somewhere over there, okay? N over h EB. This is replaced by some filling factor in which I would like to decide that there is an effective magnetic field, because certainly the number of fermions has not been changed. We are changing the orbitals, but electrons do not disappear. There are as many composite fermions as there are electrons. So I will decide that they fill some flux V star. So it means that this nu star is 1, while we have the filling factor, which is 1/3. So it's equivalent, if I write this in terms of magnetic field, by saying that the magnetic field felt by composite fermions, it's B minus 2n phi naught, where phi naught, I've written it somewhere, I think somewhere up there. Phi naught is h divided by E. So the idea of reduced magnetic flux gives us, so it's still fully heuristic, it gives us the following idea. Maybe if the flux is enough reduced, we can again find a situation in which we have an integer number of levels that are exactly filled. Because we know that in the integer quantum Hall case, filling an integer number of levels leads us to a situation in which we have this quantized Hall resistance and zero longitudinal resistance. So let me write down the relationship between nu and nu star. You see that the inverse of nu is 3. So this relation translates in 1 over nu star should be 1 over nu minus 2. So that for filling factor 1/3, we have nu star, which is unity. If now we decide, so you see that it can also be written as nu, which is nu star over 2 nu star plus 1. Yes, it looks correct. if now I fill an integer number of Landau levels for these composite fermions, I should see that there are equivalent fractional quantum mode states for p en 20 2p plus 1. So that's a very simple consequence of the idea of making these composite fermions. So this is absolutely ready to explain the fractions I've written here for p equal 2, 3, 4, and so on. If we want now to do something quantitative, we want wave functions. After all, we have the Laughlin wave function in the case of 1/3. How can we write wave functions for the composite fermions? Well, now the idea is very simple. If we are in a situation where we occupy several Landau levels, in the Slater determinant that we construct, we also use wave functions for excited Landau levels. So we go below these wave functions. Hop. Yes, please, please.
So in this argument, so far interaction didn't enter. You basically write variational.
Absolutely. No, that's right.
Is it like known what, I mean, you obviously need repulsive interactions to justify nodes, but how strong they should be, how they should decay, or is there any argument?
No. The truth is that once we are able to write down the wave functions, we can compute numbers, okay? We can compute energies, compare these energies, obtain excitations energy, but you don't know before that. For example, you can observe that if you look at the excitation gap above the ground state, which is the fundamental quantity that governs the dissipation, this gap, it goes down as 1 over p, the number of composite fermion Landau levels. But we cannot show that from first principle. We just have to compute it directly from the wave functions. So it's only a partial explanation because we have wave functions from which we can extract numbers. In fact, any numbers we want, okay? But anyway, you can feel that there is some piece which is missing. There are other theories that are not based on composite fermions that may give you some numbers, but that do not contain the level of explanation which is included in composite fermion stuff.
Can I just make
yes, please.
Very quickly. But you don't even have a variational parameter, right? So
exactly.
So that's
yes,
that
yes.
would couple to your
yes.
thing.
And that's something. Yes.
Parameter.
No, that's right.
Mystery of, yeah.
And the mystery is very deep. Well, deep, I don't know, but there is something incredible, is that you can play a lot with the Hamiltonian. You can change it in many ways. You will recompute energies with this trial wave function without any variational wave function, and it will work. You will obtain very nice energies, and more importantly, very nice level ordering. Because in the spectra, when you look at the quantum numbers of the spectra, really the level ordering is really the signature of the physics of the state. And it works very well for reasons that we don't really understand, because indeed there is no variational parameter. Absolutely. So if you want to occupy higher lying Landau levels, then let me write the wave functions will have some index, which is the index of the Landau level, and of course, an additional index which counts the degeneracy inside the level itself. And it's no longer simply a function of z. I will not write it because there is a formula in terms of Hermite polynomials. So it's a polynomial in z bar times the Gaussian. So you make Slater determinant out of this. Okay, you add the Jastrow factor, and that's it. You obtain a function with which you can compute everything, and it works. So that's the magic of composite fermions. What can I say about that? So, oops. Okay, let me use it like this, maybe. Okay. Okay. So you see that we have a way to produce explicit wave functions, and it gives us a very successful explanation of the fractional quantum Hall effect. Okay. Okay, thank you. It explains many of the features of the fractional quantum Hall effect. Not all. Not all fractions are simply explained. The fractions that are directly explained by this picture have the form p over 2p plus 1, which I have tried to explain. And there is also fractions that are of the form p over 2p minus 1 that are simply explained when the flux acting on the composite fermions is reversed. So that's simply a complex conjugation of reversing the flux. It's the same kind of explanation. There are fractions beyond that for which we may have explanations, but they are not the most prominent fraction we observe in nature. So let me now go to the second topic. Okay, I'm forced to erase this blackboard at least, and discuss a bit about this phase coherence story. Now I will discuss a little bit the case of spin. All what I said before was true for spin polarized states. Which means that if really I want to write down the complete wave function, I should say, in addition to the position of the particles, I should say also what is the spin state. So it means that the Laughlin wave function we discussed is equal to this product of factor to the power 3. I will not write down the Gaussian factor because it's here all the time. So we will simply, by simplicity, ignore it and just remember at some point that it is here. But it's universal. This doesn't depend on the wave function, so I will omit it. So then I put all fermions up. So that's the full wave function, including the spin degrees of freedom. Okay? So it's a spin polarized state. But now, so in the real world of gallium arsenide, it is known that the G factor, the Landé G factor that governs the coupling of the spins to the external field, is not that large. If you compare the Zeeman energy to the cyclotron energy, you find that the Zeeman energy is only a very small fraction of the cyclotron energy. So spin may play a role, and it's important to understand what happens if you include spin. So let's try to reason in the case where there is no Zeeman energy at all. So the limit of 0 Landé factor. So you may think it's a theorist's fantasy, but that's not the complete truth. In real semiconductor, you can tune the Landé factor by putting some hydrostatic pressure on the sample, and it's perfectly feasible to be in a regime in which there is no Zeeman energy. So that's certainly an important physical case. So we know that the Coulomb energy, the Coulomb interaction, is invariant by a rotation of the spin. So there is an SU2 spin invariance. So now let me concentrate on the integer case. Okay, we forget about this Laughlin stuff and composite fermions and so on, and we focus on the integer quantum Hall effect, for which the wave function it's this guy times a spin polarized state, okay? And that's the Slater determinant. So I will make the simple chemistry-like drawing in which I fill exactly all orbitals with a spin up. Okay? So that's the state, that's the quantum state for filling factor unity. And Coulomb interaction is invariant by spin rotation. So imagine that, so in the real world, there are higher lying Landau levels. Imagine that I just look at the lowest Landau level, spin degenerate, but just the lowest Landau level. So in solid state physics, it's common to say that we neglect Landau level mixing. Okay? Now I claim that this guy, it's an exact ground state of the full Coulomb problem, which is nice, because after all, that's what we want. How can that be? The reason is very simple, is that you take the Coulomb Hamiltonian, you write it down in second quantized language. Now, you annihilate two fermions in this. You know that you should first annihilate two particles and recreate two other particles, okay? You annihilate two of them, they are, of course, spin up. Otherwise, it's zero. Then now you have holes, but Coulomb interaction conserves spins. So the particles you are forced to recreate should be spin up. So it should be the same state. So this guy, it's an exact eigenstate. It has some non-trivial energy, which you can compute very easily. It's simply the Hartree-Fock value, because this is a Slater determinant. So it's a very simple case for which Hartree-Fock approximation is exact, and the ground state is a Slater determinant. Although in general, of course, the ground state of a many-body problem is never given by a Slater determinant. But that's the case. Of course, all this reasoning is based on the fact that you don't consider higher lying Landau levels, because, of course, there are virtual transitions to the other levels, and the whole stuff breaks down. Anyway, but we are quite happy with that, because we have a state which is the ground state of something decent, at least. Okay. Now, the Coulomb interaction conserves spins, so states should be classified by multiplet of the total spin, including this guy. And this guy, we know that, let me call SZ the projection of the spin on the arbitrary z-axis. The total SZ value is plus 1/2 times the number of particles, because we can write it directly. And since Coulomb interaction is SU2 invariant, necessarily this guy is a member of a spin multiplet of the total spin, and this total spin should be equal to this value. So it's a multiplet with total spin value S, which is 1/2 of n. So there is a whole set of states that are degenerate, that can be generated from the highest spin value by acting with the spin lowering operator. So there is no mystery in that. It's simply a quantum ferromagnetism. Here we will say that this is quantum Hall ferromagnetism, because there is a real space part which is given by this simple product of factors. So we have quantum ferromagnetism. Ferromagnetism. Okay. Okay, so now you can try, so in nature, as I argued before, you can try to be in a situation in which you are able to set the Landau factor to 0, in which case there is no Zeeman energy. Fine, that's one situation, which is not generic and which is a bit difficult to observe. But then there is another physical situation which is very close to be described by this type of state. It's the case of bilayer systems. By bilayer systems, It's physical systems in which you have two electron gases in planes that are parallel, separated by some physical distance d. So, of course, in real world, you start dealing with very complicated systems. You may have tunneling between the planes. I will consider systems in which there is zero tunneling between them. It's only some part of the wide parameter space which is available for us to study. But I will just concentrate on the zero tunneling case. If you put a magnetic field on top of this, then you may be in a regime in which the two electron gases enter the quantum Hall regime, in which case you should compare the distance between the planes to the magnetic length. And you may expect that something will happen when the distance is of the order of the magnetic length as a function of the magnetic field. So that's the regime in which I will describe now. So strictly speaking, it's a complicated systems because electrons have a spin, which may or may not be active. And then there is also a layer index, okay, because you are dealing now with a two-component system in which electrons may be in the upper or lower layer, okay? When electrons are in a given plane, then the Coulomb interaction, which is intra-layer interaction, it's simply 1 over r. So E squared over r, that's Coulomb. It's 3D Coulomb, because while the motion is concentrated on a plane, then the line of flux of the electric flux are not concentrated on the plane, so it's really the 3D Coulomb interaction, which is at work. And if you look at electrons that are not in the same layer, then Coulomb interaction is modified because the distance between the planes should be included. So we have a system that may be 4-component in the worst case scenario, in which you have spin on layer index, okay? So I will concentrate on the situations in which real spin is polarized, but the layer index is active. And I will think of the layer index as a pseudo-spin index. So the layer index is some kind of pseudo-spin. If it is pseudo-spin, and of course you want to recycle immediately this stuff about ferromagnetism, exact Slater determinant, and the like. But then it doesn't work, because now you don't have SU2 invariance in the pseudo-spin index. Okay? No SU2. But there is a symmetry, nevertheless, which is part of this SU2, in the sense that in the situation, in the absence of tunneling, there is conservation separately of the number of electrons in the upper layer and electrons in the lower layer, which I will decide to increase the confusion to use the spin index as before. Okay? In the absence of tunneling, they are separately conserved, which means that there is n up minus the n down, which is conserved. And of course, the addition, which is the total number of electrons. So the difference, if you look at the SU2 point of view, it means that since this is conserved, it means that there is a U1 invariance. The subgroup of SU2 generated by SZ, the Z component, because SZ, it's essentially 1/2 of n up minus n down. So there is a U1 invariance. If now we look at the ground state of the system, when d equal to 0, so the situation which doesn't happen which is never true for layers. So D equal to 0, we have SU2 invariance. So that's D, while for D non-zero, this is broken down to this U1 symmetry. If you look now at the fate of this many-body multiplet, when D is equal to 0, we have this complete degeneracy. And this is the degeneracy. You are moving along this set of states by using, so let's see, this is SZ tot, which is plus 1/2 of n. I will act with S down tot to some power, and varying this power, I will move inside this multiplet, okay? If I put D, which is non-zero, then this degeneracy is no longer true, okay? SZ is still a good quantum number, so these guys remain eigenstates of SZ, but they are no longer degenerate. They are no longer related by symmetry. What is known to be true is that this picture I draw is for a finite system in which you have a finite number of electrons. When you go to the thermodynamic limit, something very interesting happens, is that these guys, then they are again all degenerate while not related by the SU2 symmetry. They all became degenerate. And that's, they all became degenerate, and that's a very interesting situation because this set of degenerate states that are not, it's unrelated to the SU2. This is the hallmark of symmetry breaking. There is spontaneous symmetry breaking of this U1 factor. The ground state of the system, one possibility would be to say, it has to do with this guy, which is the lowest for any finite system size, which is the state obtained for SZ tot equal to 0. It's the lowest energy state for essentially a capacitance reason. When there is charge imbalance, it means that you are charging the condensator made by the two plates of the two electron gases, and there is an energy cost due to that, which is minimized when essentially there is the same amount of electrons on the two sides. So that's why this guy is the ground state for a finite system. This guy is quite easy to write down its wave function in coordinates. You see that you should apply an operator in which you switch the layer index, okay, on half of the electrons. But you don't do anything to the special part of the wave functions. You just change the spin index, okay? So for half of them, you put them in the other layer, but you don't do anything to the wave function. So let me call, okay? Let me call Z the coordinates when you are in the up layer, and W the coordinates when you are in the down layer, okay? So when I'm right in the middle of the multiplet, so half of the particles are in the upper layer, half of the particles are in the lower layer, okay? And nothing happened to their spatial wave functions, which means that I know the space part of these two coordinates. There is Zi minus Zj for the coordinates in the upper layer. There is a factor which is Wk minus Wl for the particles in the lower layer. It should be there because I'm just dealing with the spin index. And then the remainder, it's simply the factors that involve particles in the two different layers, I, K, let's say, okay. And this is the remainder. And that's this guy. It's exactly given this. And this guy is an exact eigenstate of the Coulomb interaction when d equals 0, not otherwise, okay? So that's a very nice wave function. You see that it starts to look very much like a generalization of the composite fermions in the case of spin. So this function has a name also. It is called the Halperin wave function. And provided you read the powers here, which I, of course, did not indicate, which is 1, this guy is called a 1-1-1 wave function. And you guess that there are, of course, immediate generalization in which you put a 3-3-3. Okay? That will be something which is close to describe the situation in which you have Laughlin correlations in each layers. Okay. So, fine. So this is the ground state when S equal to 0, one member of the multiplet. And before writing down this wave function, I was arguing that the fact that all these states become degenerate when the system becomes infinite, that's the hallmark of symmetry breaking. And this is exactly the situation in which you break a U1 symmetry like in superconductor. So there is something super going on in this business. So let me describe it exactly. Here we used the z coordinate, but of course when you are in the SU2 case, it doesn't matter which axis you choose. So instead of let's say, so S total equal 1/2 of n. It's degenerate when you have only SU2. So I could have chosen the quantization axis to be along x. So let me write it in second quantization. K is an index describing the Landau level, degeneracy, whatever it means. I will not precise it. And I occupy all the states, so that's the filling of all orbitals. And instead of putting all them into eigenstate of Sz, I decide to put everybody in an eigenstate of Sx. Okay? So x plus, which is the same as writing this as k up plus k down, acting on the vacuum. Sorry, I forgot the vacuum. Let me look at this guy, okay? This guy, now, if you look at n up and n down, they are not fixed, okay? Sz is not defined for this member of the multiplet. If you compute the mean value of Sz, then you will find that it is 0, of course. Okay, nevertheless, each of the states has z-axis 0 projection. Okay, but you see that this eigenstate, it's built upon all the members of the multiplet, and it's a state in which you have, it's the mean value of n up equals to n down. Of course, here I wrote this with x direction, but x direction is arbitrary. I could put any direction in it. So in fact, I can do the same with the direction phi in the xy plane. Add it here. And this is again a state in which Sz total is 0. It's again true for this guy. Let me call it psi with a phi dependence. this family of state is the conjugate of the family of state degenerate that has exactly all the values of SZ. Okay? So it's exactly the phase conjugate to the difference of the number of particles. So it's exactly the situation of superconductivity in which we break the U1 symmetry, where the phase is coupled to the number of particles. Here it's the same case, while the phase is coupled to the difference of the number of particles. We are in the situation of spontaneous symmetry breaking only if this set of states becomes degenerate. That's an energetic statement which may or may not be true. It's not automatic, it's interaction dependent. In fact, if we want to check this, we find that it's true up to some critical value of D. This spontaneous symmetry breaking happens up to D of order 1, D over L. There is a critical value which is close to 1. There may even be some intermediate phases that will be debated probably forever. But anyway, when you are below this phase, you can check that all the states of the multiplet becomes degenerate. This is what people from spin physics call a tower of state. Here it's a simple U1 tower of state. And in the thermodynamic limit, you are dealing with a manifold of states which you can describe as symmetry breaking with a fixed phase. So that's what is called interlayer phase coherence. Fine, so that's, let's see, obscure theory. So how can you see that something is super? Because in the case of superfluidity or superconductivity, you have the phase. You know that gradient of the phase gives you supercurrents, and there are spectacular manifestations of this phase coherence. Here it's slightly more complex because the phase is coupled to the difference of the number of particles in the two layers. So which means that the supercurrent is neutral because it should involve motions of electrons which is opposite in the two layers. So you will not see it in ordinary transport phenomena. But there is a simple way to do that, which is okay if you are able to separately make electric contacts with the two layers. And there are beautiful experiments that were done by Jim Eisenstein in which he was able to construct a situation in which you can observe counterflow. In the counterflow stuff, so you inject intensity, so it looks like ordinary Hall effect measurement, but in the end, you put back the intensity in the upper layer, let's say this is the down layer, in the opposite direction. You do that, and then you are able to measure the whole voltage in the upper layer and the whole voltage in the lower layer, V all up, V all down. Okay. Here, that's a situation in which the current flows exactly in the counterflow situation, in opposite directions in the two layers. Now let's measure the whole voltage as a function of B, the magnetic field. If the layers are very far apart or the temperature is too hot so that the correlations are negligible, then you find a simple law for the whole resistance, which is a straight line. Okay. So let's say this is the upper layer, this is the lower layer. So the current is flowing in opposite directions. So you find all oops, should be a straight line, huh? Okay, so in the upper layer you find a straight line. In the lower layer you find a straight line with the opposite slope. Now, if you are in the situation where D is quite small and you are able to have this phase coherence, this phase coherence happens only at the filling factor unity. Okay, this was all created for filling factor unity. When B is right at the filling factor unity, then I claim that these two whole voltage should go to 0. Okay, simply because the object which is moving, it's neutral. Because you have an electron in one layer paired with a hole in the other layer. That's the wave function which I wrote here. Okay? You can perfectly decide, you make a particle hole transformation only, let's say, on the lower layer, and you can see that as an exciton condensation of one electron in one layer on a hole in the opposite layer. And this guy is neutral. So when you are right at filling factor unity, the guys that are correlated between the two layers are neutral. So there is no hole voltage. So these two curves should go to 0 in perfectly symmetric ways. And that should happen precisely at filling factor unity. So that's the direct experimental proof of the buildup of these special correlations, which is related to counterflow, really to opposite currents in the two layers. Okay, in the remaining 5 minutes, I'm going now to speculate a bit about the fact that we may hope to observe these two phenomena at once: formation of composite fermions. As we saw before, these are entities that are fermions. There's the same number of fermions as in the original case. And these fermions, they may undergo the same physical phenomenon as electrons, so they may very well also themselves undergo interlayer phase coherence. Okay? So what we can do, which is quite simple, which I briefly mentioned, is that that's here. If we start from this set of ferromagnetic wave functions, we were able to write a wave function, this Halperin wave function, that describes layered correlated state, this psi 111. And of course, we are ready to play the same game of writing down the van der Monde determinants that are given by these factors. And in these van der Monde determinants, we can add Jastrow factors, so we can build up new correlations. So there is a generalization of composite fermion wave functions to the case of layers, in which we populate the upper layer with some composite fermion wave function, psi CF, whatever it means, for filling factor, let's say n up, times a composite fermion wave functions for the down layer, coordinates which I call W. And then you see that when the layers are correlated, if the layers are uncorrelated, then that's the end of the game. But if they are correlated, you see that plausibly you can have many body states with or without interlayer phase coherence in which you add such a term to some power. Z minus W times M. So this gives us, again, a set of trial wave functions without any trial parameters. They work quite well for Coulomb interactions for reasons we don't fully understand, or we can even say that we don't fully understand at all. Okay? And then we have a set of wave functions, and we will predict that there are fractions, incompressible states, states with a gap, when we are dealing with gapped composite fermion states and this Jastrow factor. Alors, let me... no. Non. Celui-là est fixe. Ah oui, oui, c'est vrai. Okay. Okay. So this set of wave functions, very briefly, you have to compute the filling factor, okay, by whatever means you find convenient and simple. Let me just in the case of the composite fermion wave function that I discussed before, I just say that if you look at fractions of the form n of 2n plus 1, with n it's an integer number of CF Landau levels, these fractions are experimentally the most prominent, which means that these are the fractions for which the gaps are the largest. If the gap is the largest, then you don't have to go to extremely low temperature to observe dissipationless transport and associated quantized Hall resistance. Okay? So you expect that if you have trial wave functions that are descendant of the states that are strongest, it's plausibly, but again, we don't have any precise recipe of why, it's plausibly that we will find states that are easy to observe. Okay? If you take such a wave function, you find that the total filling factor, let's say I put m, okay? So let me look at situation in which the layers are filled in the same way. So the filling is the same. And I will call it n. If I take this interlayer coherence to be 1, then it gives me a set of fractions which is of the form 3n over 3n plus 1. I will not give you the full zoology that you can observe. And many of these states have been observed. So these are fractions that you don't observe in any of the single layer case. And they have been observed in situations in which the distance between the layers in units of the magnetic length is of order of 0.1, which is a situation that was observable only recently with graphene devices constructed on purpose, while all the studies that I briefly mentioned, like the counterflow experiment of Eisenstein, were done in devices built upon gallium arsenide samples, for which D over L is quite close to the critical value of unity. With the creation of new graphene devices, people were able to access experimentally a regime of very small distance between the layers and observe many of the fractions given by this. So maybe that's not completely surprising because it may be explained directly by the wave functions we know. We know that the composite fermions wave function, they do work very well, even though we are not sure why it works. But in fact, people have observed fractions that go beyond that. You can try to mimic what you observe in such a setup by deciding what would be the fraction of the composite fermions for which there is the full fractional quantum Hall effect observed. And beyond that, people have observed, so observation point to fractions for which the filling factor of the composite fermion is fractional, so nu star fractional. And that's an embarrassing situation because we know that it happens also in two-dimensional electron gases. for an argument which is the hierarchy argument, for which when you have a quantum Hall state, it has excited state, charge excited state with fractional charges, something you can compute with composite fermion wave functions, by the way. But anyway, excitations on top of fractional quantum Hall states, they are charged particles, so they will fill the magnetic field, they will form Landau levels, they will repel themselves, so they are ready to reform another fractional quantum Hall state. That's the hierarchy picture, which sounds conceptually nice, but which is technically atrocious because we don't really can manipulate wave functions of wave functions. And the idea of the composite fermion constructions was essentially to resolve this hierarchy stuff by constructing explicit wave functions. So it would be bad to resurrect this idea by turning again to the idea that for fractional new star, we have again new fractional Hall states, but for effective quasi-particle coordinates, which we can't manipulate. So that would be bad. Nevertheless, these fractions are observed, and they are as numerous as the fractions that are directly included in such a sequence. And that's something which is troubling for this set of arguments, I would say. Then this is the case when the fraction is odd. But there is also the case in which people observe that the new star is an even fraction. And then it starts to be a bit complicated because it may be the signature that we are entering this interlayer phase coherence for composite fermions, because in the case of interlayer phase coherence, the filling factor of each layer is 1/2. It's nu total, which is unity, and SZ equals 0, the magic state, corresponds to exact filling of the two layers. So the filling factor is 1/2. So this is observed. So maybe that's a case in which we are dealing with interlayer composite fermion stuff. But then it's hard to characterize. It will be hard to write down wave functions. We don't really know how to do that because, again, we are facing the problem of making wave functions of wave functions, which you cannot really do. I mean, you can dream that it exists, but you cannot manipulate it. And then you should be able to make the equivalent of counterflow measurement, which is measuring the quantum Hall effect separately in the two layers to observe exactly what are the correlations between the layers to see if there is a state with interlayer coherence or not. Okay, so I will stop here after this rough panorama of the physics of the fractional quantum Hall effect. Okay, thank you.